He was saying something like, whenever a transaction comes in, it always goes right into the DAG, no questions asked. And then like later, if a conflicting transaction like a double spend or something comes in, then one of the two conflicting things is later just like, line item crossed out. Like it doesn't even make that block invalid, or it doesn't mean that block can't go in the DAG or anything. Just somewhere later in the DAG there, it's recorded like, hey, by the way, that conflict that we all clearly see in the DAG now, this is how it's resolved. This is which one of the two is the real one that's official.
Oh, interesting.
So it kind of made sense because I was thinking about it like, it's kind of coincidence. I listened to this this Epicenter last night. It's an old one that I re-listened to about. I listened to it because I thought it was mostly about Ghost, but it's not. It's mostly about something that the Ghost people came out with later that they called Spectre, and they were saying like, imagine Bitcoin where the rules are slightly different. Even when transactions come, like double spends or whatever, just imagine they go right in the blockchain. Like, in reality, in Bitcoin, they say like, well, only the earlier one's going to count. So we're going to save the space and not even bother putting this one in the blockchain. So like, blocks with conflicting transactions, at most one of those blocks can go in. But it would still work perfectly fine if we put the conflicting ones in, and then everybody, when they look back at their blockchain, can clearly see like, oh, this one came in an earlier block. It's the real one. The later one would have been thrown away. Sure, we still have the data hanging around, but we know it's invalid. So it almost sounds like that's kind of similar to how Casanova's doing it.
Yeah, cool.
Hey, there's Derek. Good morning.
How's it going, Derek?
Good morning. Sorry.
Hey, thanks for joining us so early.
Yeah, let me put a shirt on. Really quick.
Oh, that's too bad. I liked the view. So, Jim, have you met Derek before?
I don't think so. Well, greetings.
Yeah. Derek, are you still sitting there, or did you step away to get a shirt? I think you stepped away first.
Yeah.
Yeah, cool. I'm going to see if I can drum up some support from, I don't know, Jeremy or Tomislav.
Oh, yeah, cool. Yeah, of course I'm having like, I feel like Fridays I always have internet issues because I'm having like connectivity problems with my laptop, and desktop doesn't want to go on Zoom now for some reason.
All right.
All right. There we are.
All right. Hey, man. So Jim is our host here. He runs this room, and he runs CoLab, and so we hang out here and do academic stuff and Rolang stuff and all kinds of stuff. And so by way of introduction, Jim, Derek works at Pyrofex and is one of the authors, along with Mike and Kyle, on the Casanova paper and a bunch of other cool stuff. But Casanova is our focus.
Before, Derek?
Sorry?
Have we met before?
Were you at the Archon 3?
Yeah,
you were. Okay.
We may have
met there.
Well, good to see you. Thanks.
Likewise.
Yeah, cool.
Everyone's thrilled that you joined us. Awesome.
Yeah. So, Derek, we've spent some time looking at Casanova paper together as a group, and then also Isaac and I spent some time reading over it. So I think people have maybe the beginning primer, and I shared that blog post that you wrote. But I wondered if maybe just as a place to jump in or get going, maybe you could tell us a sentence or two about Casanova, or get us started with whatever part you think is interesting.
Yeah, totally. So Casanova came as we were thinking about Casper post Pyrofex, our chain split. And in particular, we're trying to prove liveness, Casper liveness. And it sort of evolved out of there. So Casper builds on, Casper uses a DAG, but still builds a chain. And so it chooses branches of DAG. we originally were going for that, and then realized, that we wanted to build it out in a DAG. Because of how it sort of started, it resembles certain pieces of Casper, but not all the way. Its main, besides its building blocks on a DAG, its other main feature is that it's optimistic, in the sense that it's more about recording transactions than resolving them, unless there are conflicts, and then it will resolve conflicts. Anyway, I think that's probably my little summary.
Yeah, cool. Okay, good. So reading over the paper, like I started to get a sense. It was hard for me to imagine, like, what does it mean? Because I get it at a high level. That, like, I think the phrasing you used in your blog post was like, we only boot up the expensive consensus forming mechanism when it's necessary, which is a small part of the time, right? So that makes a ton of sense, right? Like, don't spend all that compute and bandwidth, like, getting consensus if it's not needed in most of the cases. And so at an abstract level, that made sense. As someone who's mostly familiar with Casper, what I didn't really understand immediately was, like, and maybe I still don't know exactly how to answer this question, but I'm starting to get a sense of it. So the question is, like, what is it that Casper does routinely that Casanova is able to dispense with? Like, what does it mean in Casper to be booting up all that, like the expensive machinery for every transaction, even if there's not going to be double spends?
Yeah. Casper will, so I don't think Casper is quite as message intensive as other algorithms will be, and so that's good. Lots of algorithms require 3 rounds of messages for any block, and it's just crazy. What Casper will be doing is, if there are conflicting branches, computers will have to keep track of, like, these scores on each branch to know when to apply the ghost rule, and we'll have to periodically repudiate. So it's Casper is probably not so expensive. The way I see Casper as very similar to the Ethereum Bitcoin current sort of consensus, where you just sort of get blocks, and then if there's one chain that's longer than another, then you go with the longer one. Except for just adds a little bit of repudiations, and people can be weighted based on their stake in the network and things like that.
Yeah, right. Okay, so I know, like, with Bitcoin, if there's in Bitcoin we're forming I guess we call it a blockchain because we're ultimately only going to care about one main chain. In real time, it looks more like a tree, right? Where there's this forking near the end. And then our goal that we achieve with the proof of work consensus is, of these, like, splits and these multiple tips, we need to choose a real one and then call that one and all of its ancestors the chain, and the rest of them orphans. And the rule there is, like, if I double spend a coin, maybe I send a coin to you and then I try to send the same coin to Tomislav, then only those 2 transactions, if they go in 2 different blocks, only one of those blocks ultimately ends up in the Bitcoin blockchain, right? Because the transactions conflicted, and so only one of them was allowed in there. And then the big expense there is that, like, okay, so we're throwing away one of those blocks because I put an invalid transaction in there, but that also hinders, like, the other 1,000 innocent transactions that were in that happened by poor luck to be in my same block, and now they have to go through the whole consensus forming process again, right?
Yeah, absolutely.
So what would that look like if it were more optimistic, or if it were a little bit more Casanova like?
Yeah, so what Casanova does is, as these conflicting blocks form, it will run consensus, and the network will decide on one of the conflicting transactions. And then instead of rejecting the entire block, it just line item vetoes the transactions that were the problem ones that they decided against. So the rest of the block will still get included into the DAG. And so the problem with not using a DAG and using just a chain is that you are going to have these branching trees at the end of your chain, and if you are building a chain, you inherently can only choose one of those branches, so you lose out on other blocks. So maybe the main thing there was if it decided if we could build it out in a DAG instead of a block, instead of a chain, then you could be more selective about what you throw away.
Yeah. Okay, right. So Casper does the DAG thing too, right? And we've spent a lot of time in here because like when we started this group, we were kind of all new to Casper and like learning it from the ground up. And one of the things that we spent a lot of time getting ourselves to understand is how the scoring works and how the ghost rule works. And I actually got myself confused reading Casanova for a while because I think you guys have a notion of score in there, right?
There is,
and
yeah.
Score is similar to how it works in Casper, but what I was confused on for so long is what we do in Casper then is once we've scored all our blocks, we apply the ghost rule and we basically like traverse this DAG looking for like what's the heaviest way to go every time there's a split. And then we get to a tip and we say like, okay, that's our main parent. We're going to build our next block there. And if it happens to be the case that we can also include some of these other tips, like so that we don't have to orphan them off, that's great. And we will. But if there's conflicting transactions, then in Casper, we go straight back to like the Bitcoin way, right? We say like these two conflict. So like we're taking the main one, we're taking any that play nice with the main one, but we're throwing away all of these other tips just because of one conflicting transaction. Mm-hmm. And so Casanova does something different there, I think, right?
Yeah, it does. And originally when we were thinking about Casanova, we had a similar notion where you choose the best branch and then you include everyone else that you can. And that ran us into problems because there was always a scenario where you could time where you could delay network messages in such a way that people are constantly repudiating their and these might be edge cases and they might be like never happen in real life cases, and so I don't know if you saw like a month or two ago Pyrofex wrote this article about how Casper's not live, and they were really snarky about it on Twitter.
I didn't see that, but it sounds about. Was it Nash?
Oh man, it was Nash and Kyle. So we had been seeing these problems of if you have to make a choice on the branch and you're doing it by weight, there are ways to under your assumptions and with very favorable network conditions, there are ways to make people just alternate forever. And so I wrote up a little bit on it and was like, okay, here's the main problem. And then Nash and Kyle took it and bastardized it and made it into made it into this like really intense Casper's the worst paper. So there was some intense dialogue on Twitter. And so the way that that Vlad and then later on Vitalik responded to our claims that Casper was not live was saying that so every time we gave a counterexample, we were allowing block production and block production to be as fast or maybe faster. Like we're making no claims about the relative speeds of block production and message receives. And so most of these examples treated block production very quickly. And so in practice, that may not be a problem with Casper, but it certainly does not meet rigorous requirements of like a truly a consensus algorithm that functions on a truly asynchronous network. And presumably if one wants to scale Casper, then you'll have to be keeping track of these speeds. And even in if the network goes down, it could really affect performance, because you could get a lot of waffling while the network is having a problem sort of connecting. So anyway, there are strong feelings in that domain between Pyrofex and Vlad.
Yeah.
Which I was not thrilled about. It doesn't make for very good science, but
Wait, so you used a term there, waffling. I've never heard that before. What are you talking about exactly?
Like going back and forth on a decision. And so
okay.
So like, they may decide one and then see, I need to repudiate my last block because because I was wrong after all, and then just sort of keep repudiating and never producing a block that gets accepted by the network.
Okay.
So let me see if I understand that right. So we started out in here talking about like Casper friendly binary consensus. Have you looked into that? Like, do you know what that game is, Derek?
No.
It's basically like something that Vlad talks about in some of his Casper papers, and it's kind of like how you guys start by talking about Casanova attest, which I do want to get to soon. It's sort of like a simpler thing to wrap your mind around, and then he starts to take us into the full like CBC Casper and how to use it on the blockchain and stuff. And basically with friendly binary consensus, the idea is we have these weighted validators. They're going to send messages to one another. And the thing that they're trying to come to consensus over is a single bit, right? So we end by either saying the network has come to consensus on false or on true, or like on 0 or 1 or whatever. And one of the things that we observed there is that if I'm playing as an honest validator, just following protocol, I may at some point in the network send out an estimate of, I think the bit's going to be 1, which basically just means like, given what I've seen so far from my peers as validators, more of their weight is signaling that the final answer is going to be 1. Sure. And then maybe some time goes by and I've gotten new messages across the network from validators I hadn't heard from, or just updated messages from the same validators. And now, still as an honest protocol following validator, I can later send a message and say like, well, it turns out I've gotten more information and now I think it's going to be 0. Even I know I said 1 before, I'm not equivocating, but new information and now it looks like 0. And if you construct it right, you can make a validator have to change their mind like that several times. And so what you're saying is in Casper, you can actually set it up so that never ends and never comes to a final agreement.
Yeah, exactly. I can send you the link. You'll have to like tone down all the strong language and attacking.
Yeah. Find the math under all of the mammal social interactions, as Jonathan would say.
I do want to. My connection just got worse. Sorry.
That's okay. You're with us still.
Okay. I'm still okay. Let me find the link.
Okay.
Yeah, it's so bad. I just could not believe it.
It's almost like prerequisite to get academics on Twitter, right? You just need a certain amount of snark in the mix, or it's not going to get past the peers that review it for the Twitter journal.
Exactly. Yeah, truly. Like there was so much activity on Twitter. Oh, perfect. There it is.
Yeah. Oh, Tomislav found it. Oh, cool.
Yeah. Thank you.
I'm gonna drop it in Colab too.
So, so here, the problem that we were finding was we were trying to.
Tomislav, your mic is super loud.
Sorry.
Yeah. Thanks. Yeah, there's some mic noise there.
So the problem we were finding was we were looking at this sort of repudiation rule, and that was like the crux of the issue was like, when is it okay for me to repudiate? And at first we were like, okay, you just repudiate if you see a stronger, like a heavier chain than what you saw before. And then that turned out to be relatively straightforward to break. Again, the network we're working on is truly asynchronous, and so all we assume is that there's some bounded time in which messages will be delivered, but we don't know the bounded time a priori, and so it could be really slow.
Yeah, that was something interesting too that I hadn't seen before. So you had that I think you called it delta, right?
Yeah.
And that's like an upper bound on how long it might take. Yeah, you tell me. What is that?
Yeah, it's just if you send a message, you can assume within delta the message will be delivered. And you may have to build redundancies into your network to make sure it doesn't get dropped or something like that.
Mm-hmm.
But even then, so Casanova does allow for messages to be dropped or duplicated, and it will maintain safety, and most likely, I mean, if everything gets dropped, of course, nothing is live. But if there's a certain threshold of messages that don't get dropped, then it will be happy and live as well. So we were drawing from literature on consensus from pre-blockchain times where the network people work on is like this. They try to make as weak as assumptions as possible. And there's this famous result that says that if you assume nothing about your network, then you can always break your consensus algorithm. So you have to make some assumptions about delivery and connectivity and things like that. And so we tried to make the weakest that we possibly could, which is this asynchrony. There's some bounded delta. You can assume a message is delivered within delta. So
that makes sense. So, and I think it's important. You don't prescribe a value of delta, right? So it's not like delta has to be 10 seconds or a minute or any concrete number. We just assume that whatever network that we've basically abstracted away before we start talking about consensus, like it has this property that eventually, not even caring what the limit is, messages will get there.
Yeah, and so exactly. So there's some upper bound on message time, which the only thing that it's going to really, your message time just can't get delayed more and more every time. And so it just sort of arbitrarily gets slower and slower and slower. And so you can't get some linear or exponential growth of message time delivery that goes off to infinity. Other than that, as long as, it could be a really long time, as long as there's some upper bound. So, and, in conversation with Nash, he's commented about, so his background with Google was designing being like a network architect sort of from a hardware perspective, as far as I understand it. And so, he says you can design networks and you can effectively choose that delta that you want, and you can design networks to fulfill that delta requirement, which I think is pretty cool. But again, I'm not an expert at all in that domain. So yeah, under those very weak network assumptions, with this repudiation rule, if it was just the heaviest branch, then we could break it. And then we said, okay, then Kyle came up with this notion of safe sets. And so you'd have this scoring, and then I think
we talked about safe sets in health class back in high school. Not the same thing, right?
safe sets with a T.
Yeah. Got you.
So we came up with this notion of safe sets, where effectively it was based on based on what people knew they knew. So if I had seen someone support a block, and you support it by building on it. So I see validator A build on a block, and then I build on validator A's block, and then validator builds on me again. Then validator A, if once I see that validator A has built on me and I have built on validator A before, then validator A will contribute to my safe set. And so it's so the name Casanova comes from this old movie that I'm too young to know of, but that Kyle and everyone else thought was hilarious. I'm trying to remember. There's a funny link that. Let me see if I can find it in under 30 seconds, and otherwise I'll just send it to you later. There's this. Oh, I won't. I'm on my personal computer, not my work computer. Send it to you. It's pretty funny. But there's like movie Casanova something where there's like this funny scene between like the superhero and a villain, and it's all about like, it's like, oh, I knew you knew, and then he's like, oh, but did you know I knew you knew, and then and the guy's like, oh, well, yes, I knew you knew, I knew you knew, you know, and it's like this funny dialogue. And so Casanova, the name Casanova comes from that, because initially it was all about like, you know, what you know, other people know that you know that they know. And once you get to a certain threshold of like, I know, you know, I knows, then you can consider it safe. So that worked for safety. We couldn't branch, like we couldn't fork anything doing that. But there were instances where you could break liveness. And so essentially what ended up happening was that every time we tried to choose a repudiation rule, it was either too weak to be safe and it was live, or it was strong enough to be safe and it was not live. And we never proved any theorems about it, but we did get the sense that there was this sort of threshold of strength of repudiation that was somehow incompatible with safety and liveness at the same time. And there may be some sweet spot, and I'm sure that there's some amazing cool rule. Maybe, who knows? But so our next attempt was to make the repudiation rule, and then make decisions on repudiations that you'd have this exponential back off on how quickly you could make the decisions. And, you know, we're trying to make liveness work there. And so essentially what happens is, you know, if I repudiate a block once, I can do it right away. And then if I repudiate a block a second time, I have to wait, you know, 2 time steps or something like that. And then a third time I have to wait 4 time steps, and if, you know, et cetera. And then that way, the idea is if people are vacillating back and forth too much because the network is going too fast and blocks are being created too quickly, then it sort of temporarily slows everything down while everyone catches up and chooses the right one, and then you speed back up. I was pretty optimistic about that approach, and again, we never proved any definitive theorems, but we kept finding little holes.
Yeah, that's a pretty interesting approach that I hadn't heard of or thought of before. So my question is like, how could you enforce the back off period, you know, like in an asynchronous network where I don't know for sure what your clock says, or, you know, I got this message from Derek, but I don't know when it was authored or whatever. So how did that work?
Right. So yeah, you run into a problem. Either you have enough time in the past that you can make all these timestamps in the past, or you can make timestamps in the future, right? The way we were thinking about solving that was that if you get a block with a timestamp in the future, you pretend like you didn't get it until your clock matches that time.
Yeah, that's a good idea. That makes sense.
So there'd be some bounded time behind you that, you know, someone could slow things down and make things crazy, but eventually everything would have to be in the future, and you would be waiting. So you can force it that way. Or even some make some, you could, you know, some consensus algorithms will make assumptions about the network where you have like this like almost synchrony in your clocks. And so you say, you know, like, we can't assume we're on the exact same time, but there is some interval that will assume we're all on this time. And so if I get a block that's outside of that interval, you know, with a margin of error for delays and messages and things like that, then you could even slash people for doing something too far in the future or something like that. And that might motivate. I don't know. I think there are a couple ways to deal with that, but
do you need to know exact times or just the order of blocks? You know, who sees whose blocks and in which order?
Yeah, So Casanova is all about the order in you get an ordering of you get the order of transaction like events based on when blocks were built on top of each other. So in Casanova, you don't need to know the exact time. But if you wanted to solve this problem of repudiation, that we were trying to solve, making the right rule, then you might have to care about time. Yeah.
So you mentioned transactions and events, and that's something to dig in on too, I think. So I know like in Bitcoin, a transaction is what you send in when you want to spend a coin or whatever. I think Ethereum has a really similar notion where, a transaction, it could be spending ETH, but also like calling a smart contract or moving an ERC20 token or whatever. And then in our chain, that word got all kinds of attention for, the same kind of political reasons that you talked about earlier. But like typically in the blockchain space, sending in a transaction is what you send in to some node to say like, hey, get this in the chain for me, right? But the jargon is, I think, a little bit maybe not different, but at least more specific and more articulate with Casanova, right? So like, what's in an event, and does it ever graduate to become a transaction, or is it the other way around? And how does that work?
Yeah, good question. The paper is a bit obscure on this, and it's not straightforward to just like see what's going on. So event is meant to be more general than a transaction. And so you can come to consensus on things that have nothing to do with money in theory. And so we, make all this terminology with events and things like that, and, conflict domains of events, and in practice, they're just transactions. Unless you have a smart contract language, then deploying or calling a smart contract could also be considered an event. But certainly in any blockchain initially that's built with Casanova should probably only include transactions, and then later on sort of tack on some smart contract addition to it. But yeah, it's sort of meant to be those.
Yeah. Okay. Cool. All right. So I wanted to also go over maybe this is what you were talking about with event domains, or what was the phrase you used there? Was that
right? Conflict domains? Conflict
domains. Yeah. So there's this notion in the paper that's like script E, I guess, right? And then you index them with these subscript I. So they're, in fact, maybe I'll just share give me 1 second here. So I got Casanova stuff up here.
Nice. Yeah, I'll send you
that. and then there's this Casanova stuff too.
Which is better? That's the question.
So somewhere in section, yeah. So maybe this is where we'll start, and then if you want to point to a section in the paper, or I'm ready to draw a diagram if that helps or whatever. But so we've got this thing here. So section 2.2, it says, we assume some set of all possible events, which is this big bold E. Mm-hmm. We also assume that it's suitably partitioned into mutually exclusive alternatives. So you're basically taking this big thing E here, and you're saying like, we can divide it, we can draw lines through it to like segregate it into part A, part B, part C, or whatever. And we're going to, or I guess we'd call it like, how do you pronounce that, Derek?
Script E sub I. So yeah, there's some indexing set, capital I.
Okay, that's this guy.
Bold E is divided into a bunch of script EIs, where I comes from capital I. So capital I could be like the natural numbers or something like that. So you get a countably infinite number of script EIs. It could be uncountable. Like it's supposed to be this really general.
Yeah. Okay. So to start wrapping our minds around it, let's consider like kind of a more concrete example or use case, instantiation of this general idea. So like, let's say we're going to build some not chain, I guess, but some platform that's pretty Bitcoin-like. Yeah, we'll build some payment protocol that's pretty Bitcoin-like. There's no smart contracts. There's no like multiple kinds of tokens or anything like that. There's just one token. People pay each other with it. The dependencies are clear, right? But in order to spend a coin, it has to be paid to me first. And
Yep.
so what are elements that are in this big bold E? Is that like Joshi pays a Bitcoin to Jeremy a thing that's in big E here, or how does that work?
Yeah, we could probably construct a bold E as tuples, where the first coordinate is the state of the network, like state of everybody's sort of balances, I guess, and then the second is a transaction, is like someone moving money.
Okay, so it's not just the transaction; it's like a pre-state and then a transaction, and that tuple would be something that would go in the big E there.
I mean, in order for two transactions,
yeah, we had some network stuff there. You with us, Derek?
Oh, sorry. Yeah, that was.
Nice.
Yep, I'm still here.
Okay, cool.
My Wi-Fi at home is really unstable. Sorry.
Yeah, that's okay.
Yeah, mine too.
Yeah.
Okay. I cut you off because it started cutting you up. Like my network was down. I didn't hear what you said fully.
Oh, okay. So I was saying like we were talking about how to build this set big E. E is a set, right? Yeah.
Mm-hmm.
So and you were suggesting the transaction itself of like me paying Jeremy a coin is not sufficient to be a thing that goes in big E, but maybe the tuple of like what was the network before the transaction and then the transaction, that's sufficient to go into big E.
Absolutely.
Okay.
So in order for a transaction to be a double spend, like you need someone's account balance, and you need two transactions that exceed the account balance, and you also need to know that that the network was in the state. And the important part of the network state is that I have 100 coins and I tried to spend 100 coins twice.
Mm-hmm. Mm-hmm.
Right. So just two transactions of me spending 100 coins is not sufficient, because I could spend it and then receive 100 coins and then spend them again. Right.
Sure. Or you might have had 200 to start with or whatever.
Yeah, exactly.
So quick question on the double spending part. So like, for instance, this is just a totally hypothetical situation. So with Ethereum, to where you have to sign transactions, what would be the case if I'm not sure if there'd be, depending on the platform, there's transaction signing, but if I would have signed a transaction, got the serial number, and executed it twice, how would the DAG handle that?
Okay, let's see. So am I a user, and I'm sending to some validator the transaction. I want the validator to put it on the blockchain.
Yeah.
Is that the situation?
Like, even like, it doesn't even have to be like malicious. It can be, hey, I'm trying to test out this program, so I got the serialized and I just executed it twice. But
sure.
At the same time, that the validator doesn't know that. They could have been like, oh, this guy's trying to double spend, busting it to two different addresses.
Yeah. So there, if a validator is the one, well, okay. So if we have a user who's trying to double spend, it's not always malicious. Like sometimes transactions do go through twice, like at a store or something, and then the store has to resolve it. Or sometimes like I don't know, you just thought your balance was higher and you weren't paying attention or something. And so as we've talked about this, a pretty reasonable solution that we think is pretty reasonable is if I'm a validator and I receive conflicting transactions, this double spend from someone, I could notify them, and then if it happens again, then I could sort of have this threshold of double spends that I allow, and then I would blacklist this user and say, I'm not listening to you anymore because you give me garbage transactions. Either that, or a validator could just choose one of them arbitrarily, which may be unpleasant for a user who's accidentally double spending. If both of those make it into blocks, so if I'm a user and I send validator A a transaction and validator B a transaction, it's the same serial number and the same amount, then the network could also just say, oh, both of these validators heard about the same transaction we'll record it twice, but we only say that it went through once. So that's another way.
True. And this is where it might get tricky to where what if, the other validator didn't see it, there was like a network delay, and that just starts off the whole DAG, and then validator, 4 down the road says, wait a minute, I have 2 of the same serials. This one obviously got processed first, even though you process it. Does that mean you're just going to slash the transaction?
So I guess it depends if this is maybe a more of a like a philosophical question about what do we consider conflicting. And so if 2 transactions have the same serial number, and it's identical transactions, it may be advantageous for a user, who wants to get their transaction through as quickly as possible, to send it to several validators, so it goes through whoever's fastest. And that's definitely a situation that we've thought about, and I'm not sure that we've come to any concrete decisions about how we're going to handle that, but the idea right now is that it's fine if a transaction shows up more than once, and if it's the same serial number, and therefore, you wouldn't consider them conflicting because it is indeed the same transaction. Then you could see it a few times, but only say it happened once.
So Derek, you're kind of bringing up this distinction of it's one thing to see the exact same transaction more than once, right? Like where I say I'm paying Isaac one coin at this date for such and such, and it's coming from this part of my wallet. And if that gets in the DAG more than once, a reasonable reaction might be some like technical version of like, yeah, dude, we heard you, like we did it. As opposed to something like, you can't spend that same coin twice, like one of these has to be invalid or something, right? So there's a distinction between whether it's conflicting transactions versus the same one twice. But Jeremy's scenario got me to something that I'd like to hear you talk about, actually, which is, so imagine I am malicious now, and I do try this, double spend. And so I send a token to Isaac, and then I make a transaction that sends the exact same token that I can't cover anymore to Jeremy, and I send it to some different validator, right? Trying to get it like a different entry point into the DAG, trying to totally go around that like validator level filtering that you described. And so somehow my 2 transactions are both in the DAG now, right? Now, maybe I sent one of them to Alice, she's a validator, she puts it in. I sent the other one to Bob, he's a validator, he puts it in. Neither one of them, their crosstalk channel they haven't heard from each other yet. And so both of my 2 mutually conflicting transactions are now in the DAG. Because like you told us Casanova is optimistic, right? So they're both in there.
Yep.
So what happens now? It seemed like, from a Bitcoin perspective, it's like, dude, that's not good, right? You just put 2 conflicting transactions literally in the block DAG. That's like the thing. In Bitcoin, that's a disaster. So how does Casanova take care of that, and how does that play out?
Yeah, so that would constitute 2 members of the same conflict domain. So if we go back to this script E and EIs and the capital E, what we're meaning to communicate here is that there's this huge set of possible events off to infinity of time. So it's this enormous set, and and you're dividing it into events that could that could conflict. And so the way we treat it is there's this algorithm that we sort of build into this optimistic block DAG, which is the algorithm 2 from this DLS paper that we cite.
Should we look at that? I know you told me I should look at that, and I didn't have time yet. Is it similar to your algorithm too?
It is not. No.
Okay. Okay.
It's very different. Essentially, all it is it's saying we're coming to consensus, and what we assume is that everybody in this party that we're coming to consensus, every member of consensus starts with an initial value of what they propose for consensus, and then through some message passing, you come to the conclusion on just one of those. And so what we what happens in Casanova is that concurrently, while people are building their blocks on the block DAG, sort of built into that is this algorithm too. And so Alice got one transaction, Bob got another. They don't know the other party has the transaction. They both add it to the block DAG. And then, maybe Dean sees Alice's block before he sees Bob's block. And so he sees, Alice's transaction. And then, then everybody sort of goes getting blocks and they start the algorithm, this consensus algorithm, with this conflict domain of these two transactions, and everybody's initial value is the one they got first. And so sort of built into this building onto the block DAG is essentially you build blocks, and in the header you include relevant information relating to this algorithm too. And relating to this consensus. So in the header, you'll be like, here's my initial value. And once you notice that there's a conflict, you'll be like, this is the one I saw first. And then you'll wait till you see people's messages in their headers of their blocks as they're building. And then you sort of follow the protocol until you reach consensus on which of those two transactions you're going to choose.
Okay, so that's... Yeah, go ahead.
Where is the point when you know that block is finalized? So the validator can be sure that this is the right chain.
Yeah, you can. Oh, did I cut you off?
Well, I was thinking that when validator can be sure that the current state cannot be changed for any future message.
Yeah. So anytime I receive a transaction, essentially what's happened is that I see a transaction in my block DAG, and if it doesn't conflict with anything yet, then I could say, okay, if essentially what's happening is, if this turns out to conflict with something, then when I start consensus, if we were forced to start consensus on this transaction and something conflicting with it, then I already know my initial value. And I can see, if time goes by, I can see what other people's initial values, so if I see this transaction and then later on I see that someone else built on top of that block, then I will say, oh, Alice also saw that transaction. And so if we were to start consensus on this transaction that we have yet to see any conflicts on, then I know Alice's starting value for this transaction, for this consensus algorithm, would also be the same one as mine. And then, as time goes by, I may see a majority of people that have seen this transaction that I saw. And so, if nothing has conflicted yet, then I will say, oh, if we have to start consensus, now I know there's a certain proportion of the network that will start with my same value. So there is the threshold, which we call the fault-tolerant majority, the FT.
Okay. Is this means that you want the half of like a healthy validators to confirm your value?
It's essentially 2/3 plus 1.
Oh, 2/3.
Yep, it's just something greater than 2/3 of the network. Once you've seen greater than 2/3 of the validators in the network sort of attest to the same transaction that you attested to, then you know that if someone else who hasn't attested yet were to introduce something conflicting to it, and you had to start consensus, you already know the result of consensus because you had this special majority. And the fact that you already know it has to do with this algorithm that we're drawing from, algorithm 2, that we cite. And so you never have to start consensus. And at that point, you can say, okay, this transaction is finalized because whatever happens, whatever happens, we don't even have to start consensus. We already know the result of consensus.
Why is 2/3? If you have more than 50%, why is this not enough?
Yeah, so we assume in this model, we assume that up to a third of validators can be malicious, and so that is sort of the gold standard of safety. Is like you can't ever expect to be safe and live and go above and be able to assume that more than 1/3 of your validators are malicious. And so to have safety and liveness, that's the upper bound. And so we assume the worst case. We say up to a third is malicious.
That's for Byzantine tolerance, right?
Yeah. So that's for Byzantine fault tolerance. So sorry, it's not up to a third. You have to have less than a third. So you can't have one.
So that's okay. So when we've read this before, we saw FTM, and I wasn't sure what fault tolerant that it meant. I didn't know that it meant fault tolerant majority, but that phrase makes a lot of sense. And so basically, you're saying like, yeah, if everybody's being honest and following protocol, then it's half. But the whole point is we don't know that everybody's being honest, and in general, there might be up to a third, Byzantine actors here. So what we really want to do is make sure that we have at least half of the honest.
Exactly.
Yeah. And so that gives us, so if we assume the worst case, a third of them are Byzantine, then we need half of the remaining 2/3 to be on our side here. So that gives us 2/3 overall.
Exactly. So yeah, if you do have greater than 2/3, then half of the ones that you have may be malicious. But you know that at least half of the honest nodes will agree. Mm-hmm. So consensus, you can say what consensus will result because you have an idea of how many honest people there are.
So that answers one of. Oh, sorry. Go ahead, Isaac.
No, I was just going to say that, and this is all specifically in the domain of asynchronous consensus protocols. And this all goes back to some stuff that we were talking about. I think in the second meeting we ever had for this study group, when we went through this kind of like a sketch of this proof of the 2/3 fault tolerant majority.
Yeah, cool. Okay, so Derek, you do have a notion of finality, it sounds like then.
Yes.
Right. There's a point where I know for sure that my transaction will never be reversed, even if I do my best to double spend it and convince people that the new one's the real one. It's far enough up the DAG and enough people saw it as the first of the potential conflicting ones that it's finalized.
Yeah.
So can I say what I understood of what you were just saying?
Yes.
So you're saying now if 2/3 plus one of the validators have seen a particular transaction, it's finalized.
Yep.
Okay.
Yep.
And not seen any conflicting ones, right?
And not seen any conflicting ones. Yeah, sure.
Yeah. So if there are conflicting, then consensus will run, and once consensus is done, then it's finalized.
Right.
But if I'm a user, so validators themselves will probably not keep track of what is and is not finalized. Users would probably just look, and once they can, if I'm concerned about my transaction, and once I can see that enough people saw it, then I can be like, oh great, now it's finalized. Now I can move on. So there is a time bound on, if everything is going well and there are no conflicts, you can assume that if you're being honest and and everything is happy, you can you can assume that your transaction will be finalized in 2 delta in that time. So if you are engineering the system to have a specific delta like this bound on message delays, then you only have to wait 2 of those to know that your transaction is finalized.
Go ahead.
So, this means that each message finalizes 1 block?
It's 1 block, and then people just have to build on it. Like enough people have to build on it like once. And once you see it, enough people build on it once, then you're done. So in theory, like if everyone is building blocks, in intervals of 10 seconds or something like that. And so, you have, tons of blocks at every level, which, may or may not happen. But then I could propose a block and if the transaction has no conflicting, nothing to it, then at the next level, people will have all built on it. And so then it will be finalized right away.
Yeah, so that makes sense too. And, for a hot second, it seems like, oh man, I'm going to have to be like mentally traversing a graph to know if my thing is finalized. But in reality, that's like a block explorer does that for you, right? And you get, it tells you like, this has met the necessary criteria or something.
Yeah. So it wouldn't be too expensive if you make the users calculate, then it wouldn't be too expensive at all.
Cool. Okay, so I wanted to, we're almost up to the hour, and we want to respect your time here. So I was just curious, like, so Pyrofex has published this, right? So at least the algorithm itself is not like proprietary information or anything. But are you guys going to be like, I don't know, approaching blockchain projects to use this, or building anything, or what? Is it just cool math? Like, I love doing math just because it's cool, right? Like, what do you have in mind in that regard?
I have to choose my words carefully. I think the response I'm supposed to give is that we may or may not build a blockchain.
Okay, cool. That sounds.
So take that as you will, but the official Pyrofex response is actually, I think a more official response will be up within like a day or two. Like,
okay, yeah, cool. We can be patient for that long.
I don't,
Yeah.
So
cool. So Derek, is there anything you want to talk about that like we didn't stumble upon in the hour?
So the full-fledged Casanova algorithm. So I sent this to you, Joshi, and as this sort of second paper. So as we were doing Casanova, it became clear that that this choice of so essentially what's happening in there are 4 algorithms that we build up to the final Casanova, and the third one is we're just attesting to what we see, and then if there's a conflict, we use this side resolution mechanism. And so I would keep building, and then on the side, I'm sending consensus messages, and these are separate. And once I finish sending consensus messages on the side, then I'll know which one to choose, and I veto the ones that need to get vetoed. And then the last algorithm is instead of running the consensus on the side, you build it natively into the block DAG as you're building. And so, just looking at the algorithm, it's unclear exactly, what the motivating ideas are there, because it seems kind of hectic. But this process of going from having this optimistic attestation thing where you're just saying what you saw, and then if there are conflicts, you go to the side and you resolve them somehow. Moving from there to building it natively into the algorithm, into the consensus itself, or sorry, the building the DAG itself. That can be done with many different algorithms. Like this choice of algorithm 2 from that DLS paper is sort of a herald back to classical literature on consensus, but it is by no means the only one. So for example, a couple of days ago, we were looking at taking some elements from GoSig and using GoSig as that consensus mechanism and building it in. And there are certain things you have to do to sort of change things up, but the thing, when I see this, the thing that I see most exciting about it is that classical consensus algorithms, they require tons of messages, but they're very secure, and just the proofs are really good. Like, if you're running it on a small network, it's a very good choice. And then these more recent blockchain algorithms, many of them come without proofs of safety and liveness, which I see as a major flaw of the field. Even Bitcoin, they sort of, in the white paper, they give a sketch of a proof, and I think the proof is probably correct. But by no means do they, really dig into the math. And so what I find exciting about this is is by putting events, transactions or whatever into this DAG structure, you can take off the like this heavy cost of consensus that that classical, like this message cost that classical consensus tends to have. So the burden of sending messages is substantially alleviated, and you can come to consensus much more quickly on many things. And so there's this second paper after writing Casanova. I had this sort of aha moment with, oh, we could do this with so many other things. And in fact, this can take many classical consensus algorithms that people consider impractical because of the sheer message volume, and we can convert those into much more scalable consensus algorithms, where you need to, in any situation where you have lots of incoming things that you need to come to consensus about, and you need to do it all at once. And so, on a blockchain, that's transactions and smart contracts, but, in theory, it could be other things. And so what we can do is we can say, let's grab this old algorithm that has these really nice proofs, but has a huge message volume, and let's sort of rethink the fundamental structure. Instead of doing it one at a time in sort of like a chain-like manner, we're just going to do it all at once in a DAG. And that way you get to combine, you really cut your cost on the message volume. And the really cool thing about it is that proofs of safety and liveness are the same as they were before. Like you can, you've abstracted in such a way that you can reduce back to the original case. And so like in the second paper, it was like so nice because, it came time to prove things. And I was like, look, we just make a reduction. It's super easy. So, anyway, so that's what I see as like the main contribution of Casanova is rethinking the order in which you need to come to consensus about things, and like instead of doing it linearly, do it sort of all concurrently. You can really speed up these old algorithms.
Yeah, that's cool. So you're kind of breathing second wind into all of these good, algorithms with sound proofs that preceded Bitcoin, and now bringing them into this context and putting them on a DAG and saying, look how great not just this one we chose in Casanova here, but in fact, a lot of them can be resurrected in that way. Yeah.
So I find that really exciting. And that's kind of, since I'm just doing math because I like the math, and I'm much less of a technical kind of guy as far as like, programming goes. That is the bit that I'm most like thrilled about, and that I want to tell other mathematicians about.
Yeah. Well, it's been an honor for us to be the ones that you're telling today, man. Thanks for giving us the time to explain Casanova.
No, this was awesome. Like I'm genuinely like really grateful that you like reached out, and like super happy to talk about any of this at any time. So cool. Feel free to reach out, and anyway, thanks for having me. I appreciate it.
Yeah, thanks.
Yeah, thanks for telling us about Casanova, man.
Yeah,
cool. So guys, I'll share that second paper that he was mentioning there at the end, and then I guess Tomislav and Isaac, do you guys want to do some Haskell stuff?
Sure, man.
All right,
yeah,
cool.
Sure.
Cool. I'll find that video and send it to you guys so you can have a laugh later today.
Oh,
awesome.
Nice.
Cool. All right,
Otherwise,
thanks,
I'll just
Derek.
head out. Thank you, guys.
Cool.
We'll see you.
Thanks.
See you later.
Bye.
Thanks, man.
See you later. Nice.
Cool.
Thanks. What are you guys doing now? Should I restart the recording?
Yeah, I think so, probably.
Yeah, we should
New
stop and
topic.
then restart.
So